Okay.
Let me know when I have to stop.
Yeah, just stop there. Okay, yeah, fine. So it's better now, right?
Yes, Dorian, it's better now.
Okay. So, okay, I was talking about this Navier-Stokes equations, and so there are different representations of the same equation. So that's why the governing equations become uh, we are using a different methods, numerical methods for all those different CFD equations. So that's where it becomes critical. And also, it's not just the Navier-Stokes equation. We do some kind of dynamical approximation. For example, the Euler equation, which doesn't use the shear stress term, is also solved under CFD. And sometimes the potential equations. So a lot of different kinds of equation can be derived with the different approximations. So all of them can be classified into CFD methods as long as we solve them in a numerical way. So that's why it is defined that in this manner. And so what are the numerical methods were used? There are many methods available and are being used earlier. And nowadays it is mostly like finite volume method. That's what is used on many commercial softwares, and it becomes a kind of a standard. The finite difference method is what you find in a lot of textbooks as well, and so that is where it started. And in finite difference method, we solve the differential form of this Navier-Stokes equation. And in finite volume or the finite element method, we solve the integral form of these equations, not the differential one. And so the advantage is a lot of advantages are there in the finite volume method, which satisfy the conservations and you can capture the shocks exactly. And the finite element method it's also have a good high resolution and accuracy, but there were some difficulties in the shocks where the discontinuities are present. But nowadays, the finite element is also improved a lot after the discontinuous method. The lattice-Boltzmann method is the one which uses a particle concept of kinetic theory. So the kinetic theory of gases might know, and they try to solve the collision of the particles and get the solution. It's completely a different approach, the lattice-Boltzmann method, which is also a kind of solving the Navier-Stokes equation, but not the direct one, slightly derived from Navier-Stokes, or a compatible equation of the Navier-Stokes, I would say. It's not derived from the Navier-Stokes, it's derived from the kinetic theory, but it can be related to the Navier-Stokes equation as well. So this is what the CFD in a very, very top level. And can you go next slide? Yeah. So what are the process involved in CFD? So the first step is the geometry. So when you start doing a CFD application work, right, the first thing is the geometry. So we have to develop a geometry, or designer would provide a geometry, and we have to do the cleanup of the geometry. That is, it's quite difficult task, and it consumes a lot of time. And there are a lot of softwares available to do the cleanup. So that is the first step. And the second step is generating a mesh. So if you see here, it's a surface mesh. So we will generate a volumetric mesh also. The mesh generation is the second step. And there is, I've seen with the people, there is a lot of confusion between the mesh generation and the discretization. The discretization is something different than the mesh generation. The purpose of mesh generation is that whatever the equations we saw in the previous slide, those equations are continuous. So we are trying to solve a differential equation and the integral equation. They are continuous in nature. And those equations are valid within these small control volumes or the measure. And from one mesh to other mesh, there could be a discontinuity, or it could be different. And this is called the weak solution. So that is the primary purpose of generating the mesh. And the third step is, after generating the mesh, the third step is the initial and the boundary conditions. Okay, so where Shruti, can you move to the, or you just yeah, or just you put the full slide also. It is okay. Yeah, and the initial and the boundary condition is the next step, where we try to define the boundary condition of the problem. The boundary condition is very important because most of the times we don't solve the complete the actual cases as it is. So we try to restrict the domain of interest, and whatever the boundaries of the domain, we have to do some approximation and give the values there, and that approximation should be reasonable, and that should able to capture the physics. So most of the times, if the CFD solution is not converging, has some issues, it could be the relation problem with the boundary conditions or meshes sometimes. And the initial condition is critical for some cases, and most of the problems we solve is initial condition independent, and so it's not very critical for the final solution, but it influences the convergence rate. So if it's converging faster or slower, taking a lot of iteration, it depends on the initial condition. Sometimes it could diverge because of bad initial conditions as well. The fourth step is the model setup. So model setup is setting up the model, like numerical models or other physical models. For example, if you're solving a combustion model, then you have to set up the chemical kinetics. So those kind of things. And so once you set up the models, the numerical, there are a lot of numerical parameters out there, turbulence models, and so many are there. So once we start learning the CFD, then you will understand that so many tuning parameters or setting parameters are available. So those things we need to set up to get the efficient and accurate results. And the final one is the solution. The solution is the easiest job a person can do. Submit the job in the cluster and just wait for the solution to converge. If it doesn't converge, go back and fix. So that's where the CFD engineer becomes, the knowledge of CFD becomes important. It doesn't converge the first time. So we have to go back and understand what is the real problem and where we miss, whether we are missing the physics or numerics or something else is the real issue, and go back and fix that one and make sure it converges, and develop some understanding and standardization of what we are doing. So after the solution, the next step is the post-processing. Can you go to the next one? So there's a post-processing. Yeah. So the the post-processing is the real analysis. As an engineering work, people do the analysis, and a lot of engineers spend a lot of time on the analysis part, the designers, which actually gives the solution to the problem. The different kind of post-processing, most of the time CFD means people will see only the field data, the colorful picture as shown on the aircraft, the green color one, the bottom left. That's where people think CFD means it's just a colorful plots. Many people have that in their mind. It's not just the field data, what you are interested in. We are solving the problem at each and every control volume. And we also get the integrated solution, like the overall lift, for example, the overall lift for this aircraft, or the overall drag, or some pitching moment, or the pressure distribution on the particular section of the airfoil, which is shown here on curves, that gives the pressure distribution of the wing. So we can get any kind of information we need from the post-processing. So that is the real advantage of the CFD. So can you go to the next one? Yes. So here are the pros and cons of CFD. So what are the advantages of the CFD? So few things are quite obvious: less cost, less turnover time, relative to the experiment, and no need of scaling. This is a quite important advantage. When we're going for a scaling, we have to make sure it should be geometrically similar, kinematic, dynamic similarity, and we know that most of the time we cannot achieve all the similarity parameters. it's very difficult to achieve, and you have to do some compromise, do some correction after doing the testing. So all those things. So in CFD, there's no such need. So we can directly do the on the exact scale, and we can get the exact result. The comprehensive information, what I explained in the post-processing, we can get almost any kind of data we need from the CFD result. And the next one is hard to test problem. Some problems are very difficult to test practically. For example, in aerospace, some high altitude, so the flight goes in the high altitude. So all those high altitude effects are difficult to test. For example, if you're doing a re-entry vehicle, so those heat transfers are very difficult to test, the actual scenario of what is happening at those Mach numbers. Some of them we have to do some shock tubes or some kind of test. That is difficult. So in each industry, there were some kind of problems are really difficult to test, and those can be easily solved with the CFD. And the next one is the large design space. This is the parametric space where we can do the design. With testing, it's almost limited, but we are limited by the setup itself. Sometimes cost, program time schedule, so many things will limit the design space. But in CFD, we can explore much more. And it can also be used for the concept selection without spending a lot of money, so the cost effective. And most important thing is understanding trends. So if you want to do certain experiment, so then we can understand whether a particular variable has really an impact on your field of interest or the interest. If you found the CFD says it's not having a strong correlation or it's not of important, then probably you need not to spend time in testing those parameters in the experiment. So it is really useful in many things. Like it just gives the trends, whether it's going to increase or decrease or remain same. So all those correlation effects we can able to estimate from the CFD. And the disadvantages, the cons of the CFD is, Shruti, can you go to the next one? Yes, okay. The main drawback is it needs a validation. You cannot trust the data or the results just like that. So it needs to be validated before using any model. There should be a validation should be done. Otherwise, no engineer will trust the results directly. So that is the real drawback of the CFD. And other one is the simplified geometry. So most of the times we end up in simplifying the geometry because of the meshing requirements or some other reasons. So we don't try to model the complete geometry. So we have to simplify the geometry. That will have some impact. And also the mesh itself is a simplification of geometry. So for example, if you want to capture the curvature, then you have to put a lot of meshes, and so those kind of things are there. So the mesh usually makes the curvature flat. So there is some approximation, but usually we try to capture that by putting the more number of cells. So it's not a critical one, but that is one of the disadvantages that we have to keep in mind. And the simplified boundary condition is the other one. So we cannot simulate the exact real physical boundary conditions. Sometimes we don't know those boundary conditions. Sometimes it's very difficult to model that one. So we have to do some approximation there and understand its impact. And simplified models is like you want to model, for example, acoustics model. We don't model exactly or solve exactly the equation. We use some models to understand the impact of aeroacoustics or fluid acoustics, or the combustion models, or even the turbulence models are very much simplified. There is no direct closure that's available. So those model simplifications will have an impact on the accuracy of the solution. The final one is the computational time. So this one could be conflicting. So I put less time, less as both advantage, and here the computational time. So it's not suitable for all the problems, but in some problems, the computational time becomes mostly in unsteady problems. and the problems where you need a very accurate data, so people tend to use a LES kind of simulation. The computation time for solving one case can take almost a month or even more than that. So by that time, if in the organization, a well-established organization, you can already have test facilities or set up almost ready. You just want to build a model, probably using a 3D printing or some other techniques, and test the model, which is much more easier option when compared to solving for 1 month time with a lot of computational resources. And at the end of the, we don't know how much accurate is that also. So it becomes sometimes it mainly for unsteady problems, and it could be a drawback. I wouldn't say it is always a drawback. Okay, so this one is talking about the evolution of CFD. So the arrow mark indicates, as mentioned, how the complexity of modeling got increased over time, and the accuracy of the flow physics or the cost. So when the accuracy increases, the cost also increases. And if you see, Shruti, can you just put? I think it's better to put so that I need not to mention every time. So yeah, okay. So the first one is the in 60s. If you see, the people try to solve the linear potential equation based on those computational resources available, and they are linear equations. Potential means it's induced rotational equations. So what are those methods typically? So most of these methods, some of you might have heard. It's panel method. It's called source panel method or vertex panel method, and vertex lattice methods. A lot of methods are available, and transonic small perturbation equations, integral boundary layer equations. So all those were solved, coupling the panel method with the boundary layer equations. So all those were used in 60s, early 60s. And with time, people started putting the non-linearity effects into it and trying to solve that more kind of iterative kind of problems, where the full potential equation is solved, and with shock fitting techniques, finite difference method was got evolved, and finite difference method got used into CFD. So there is a right statement, and people started using the convergence acceleration techniques like multigrid. And so all this are for the compressible flows. At the same time, for the incompressible flows, the pressure correction techniques like the simple algorithm came into existence. So those uses the staggered mesh initially, and then it moved into co-location methods, which happened during the 80s. The finite volume method came into picture. With the finite volume method, we could do the shock capturing. That is the advantage of the finite volume method. And started using the higher order methods. Limiters came into existence, row schemes, other lot of numerical schemes came into existence, flux calculation schemes, and also on the meshing side, people moved from single block meshes to multi-block meshes and co-location methods. So all those things came. In 90s, it's like RANs. That's where the real commercial CFD started. RANs and unstructured meshes, overset meshes. So most of the things what we are using now, it's all from the 90s and beyond that. And after 2000, the CFD methods have not undergone a rapid growth as happened from 60s to 90s. After that, it is almost a kind of plateau, but a lot of different things came into picture. The wide application of the CFD started after 2000. So if you see the LDS, DNS, so all those things came, and a lot of models like particle interaction model, moving boundary measures, multi-phase. So many things came into existence, different model aspects after 2000. And on the numerical side, if you see the adjoint methods came. This adjoint method is still available in the commercial software. So some of the industries were attempting to use that its optimization technique based on the Navier-Stokes. And polyhedral meshes were already available in a lot of commercial software, which is the evolution of the structured mesh. And a lot of research are going on in the meshless methods as well. Probably in some future, we may end up with the meshless methods. And LES, some industries started using that. DNS is still distance for. And the interesting one is the GPU. This is purely on the programming side. So people started using CPU computations to the graphical processing unit. And so that gives a lot of speed advantage in the solution. And the finite volume methods started evolving with discontinued years. So it gives a very good accurate numerical schemes. And the lattice Boltzmann method came into existence recently, and even it got industrialized, and people started using in the industries. So those kind of FSI is the fluid structure interaction problems, like the flutter and buffeting kind of problems. Started using the CFD. Can you go to the next one? So next one is, I think, the application part of it. So just to bring the full slide. So on the industrial applications, a lot of industries uses the CFD. As shown here, aerospace. It all started with the aerospace industry and automotive construction. The construction industry is like the bridges, okay, and the high-rise buildings started using estimating the wind loads on those things. So there is one video, probably interested people can look into that. At Tacoma Bridge, you can search that. So that bridge got collapsed because of the excitation from the fluid dynamics. So that has given a lot of interest in those kind of civil structures, and a lot of other civil structures uses the CFD applications. And energy industries is the gas turbine, the wind turbine. So even the solar panels, the loading from solar panels, nuclear energy. So almost all the energy companies use the CFD. And the marine is it's the obvious one, the shipbuilding, marine, and other marine applications, and chemical and process industries where optimize the pipings, routes, and the heat exchangers. So those kind of things. So almost all the industries. Can you go to the next one quickly? Yeah. And one more, please. Yeah. So almost many industries, like medical industries, it's growing. Actually, the medical industry application in the medical industry has started growing, mainly in the blood flow, the cardiac. A lot of research in the cardiac area is happening. The biomedical and pharma industries also using CFDs for their processes. And also a lot of research are going on the targeted medicine. So how the medicine is carried on the bloodstream and the targeted infected area. So those kind of things are happening. Electrical and electronics, it's almost become, I think it's almost established now. Many electrical and electronics were using CFD, like a lot of electronics coolings, electrical coolings, motors, so cooling for the motors, electrical panels. So almost it is there. It's a well-established one. And industrial equipments is the other one, like blowers, pumps, boilers. So many of those design and optimization, those were using the CFD. Sports industries were also using that one. Like race car is the one which is quite famous, and it also is being used in the other, like cycling, swimming, so many different to train the sports person, and so it started being used in there. The manufacturing industry is a relatively new one, like the casting process, additive manufacturing, flow forming. So those kind of with phase transitions, right? So even those kind of models can be done with CFD, and manufacturing industries, some of the industries have started doing that one. For example, the electronics manufacturing uses the CFD for quite some time, and the other manufacturing were also started using that. So environmental is something like HVAC. So it's a typical problem in the HVAC is CFD usage in the HVAC is quite heavy. Almost all the HVAC companies use the CFD, and also in weather predictions, climate predictions. So all those industries. So there are almost all industries, most of the industries, I would say, some of them are not listed here, started using CFD. Maybe in future, after 10 or 20 years, you will see more and more industries start using CFD, and it will become the part of their process. So the next slide, I have shown. So typically what kind of application? So if the industry is using what kind of application, there are multiple applications and models they use. This is just one example. For example, in the automotive, I put some 4 applications. There are much more there, like combustion. So all are very different problems in terms of CFD, but used on the same industry or the same product. So the engine, so which is a moving boundary problem, that the piston moves and combustion happens. So it's a combustion we are trying to solve the moving boundary problem. So very complicated modeling. If you see the turbocharger, on the other hand, we don't model the complete turbocharger. We just model only the one blade with the periodic boundaries. So one blade with periodic boundaries, and just a minute. So what happened? Oh. Yeah. Sorry for that. Suddenly the application got disappeared. Where we use the periodic boundaries and solve something called multi-reference frame. So we don't actually move the boundary or the geometry or the meshes. It's all solved in the stationary coordinates, but we change the equation and add those pseudo forces like centrifugal Coriolis forces and try to mimic the effect. And so there will be like a relative frame of reference or stationary frame of reference, a completely different approach of problem. External aerodynamics, where the gross forces are the primary importance. Here it can be used for the stability of the vehicles. So those kind of applications, the heat transfer applications on the underhood. So that is the one, and something like you can solve multi-phase flows and the tank flushing problem, or HVAC. So even in the automotive passenger comfortness, HVAC becomes important zone of the application. So it's not that a particular industry uses a particular approach. So for example, the combustion is used in many industries. So if you know combustion modeling, then you can fit in many industries, something like that. So different models or cut across the industry. So that is the advantage of knowing CFD. Can you go to the next one? Okay, so this is the job opportunity part, and as I told earlier, CFD it's when I was doing, or like 15 years back when I joined for a job, CFD is not something that it's kind of, if I know its advantage, if I don't know, nobody cares actually, at least in the product industries. So that was the situation, but nowadays it's not like that. So CFD has become an integral part of the process, and you have to know CFD somehow, or even if you don't know, you will be learned within first couple of months once you enter any company. So it becomes a mandatory now. So there is no escape from CFD if you are employed in a fluid dynamic related job. It's something like become like the finite element method for a stress analysis, right? If you want to go in a stress analysis or structures job, it becomes a mandatory. So There is no escape from that one. CFD has become something similar in the fluid dynamics in the heat transfer area. And so without knowing CFD, this actually becomes a drawback. So that is the kind of situation we are going into and what's happening in the current industry. So if you look into the job opportunities, what kind of job? Can you go to the next one? What kind of job we can land, or what kind of roles we can go in? So typically, from my experience and observation, what I see, we can land in 3 kinds of roles if we are good in CFD. Okay, the first one is a developer role. It's purely used by the CFD industry, like Answers, Siemens, a lot of CFD solvers are like console, and so many solvers are there, even the OpenFoam, ESI. So if you want to go and develop the solver itself, it's a developer role. That is one of the role, and where